Hello everyone. So today we are going to discuss about uh, transmission control protocol in the computer networks. Um, so basically, TCP stands for Transmission Control Protocol, which is a transport layer protocol, um, and we used to call it as a reliable protocol or connection oriented protocol because TCP uh, mechanisms make use of connection establishment before the actual data transfer takes place. So the basic difference between TCP and UDP is that TCP is connection oriented protocol, whereas UDP is connection less protocol. There are three important phases in TCP. First one is connection establishment, second one is data transfer, and the third one is connection termination. So the connection establishment phase itself consists of a three-way handshaking mechanism. So handshaking mechanism is the process of establishing the connection between the client and server. Uh, so you guys know client, the system which requests service from another host is called a client, whereas the system which will provide the services to the host is called as a server. So handshaking mechanism uh, is very important in TCP. So before transmitting the actual data, uh, we need to establish the connection between the client and the server. So as the name suggests, TCP is a reliable protocol. So we need to send a connection request through synchronous message. See, uh, here if you look at the diagram, you can easily understand the three-way handshaking process, which involves three messages. Client wants to establish a connection with the server, will send a synchronous message, right? Synchronous message. Upon receiving the synchronous message, the server will send the acknowledgement for the synchronous message. So once the client process receives the acknowledgement for the connection request, it will again send the acknowledgement. So which means the connection is established now. So the connection is established between the client and server. Now the data transfer is ready from client to server or vice versa, right? So synchronous message is basically nothing but a sequence number, synchronous sequence number, unique number allotted by the client machine. So uh, next, the TCP header. So the TCP header field consists of various things, starting with source port address, destination port address, each of 16-bit field, and the sequence number is of 32-bit field, and acknowledgement number again 32-bit field, header length 4-bit header length field, and the 6-bit reserve bits are not used for any purpose, and the next 6 bits are used for different purpose: urgent bit, acknowledgement bit, push bit, reset bit, synchronous bit, and finish bit. And then next 16 bits are allocated for window size, the rest for the advertisement window. The next 16-bit field are allocated for checksum and urgent pointer. And then options field is not mandatory field. So you can, if you want to increase the header length or if you want to add any padding, you can use those option field. So this is the overall diagram of TCP header. Uh, TCP header uh, is minimum required size for TCP header is 20 bytes, similar to IP header. Uh, so you can increase the header size up to 60 bytes. Next one is error control. Error control in TCP. So how do we control error loss of packets in TCP? So we use three methodologies to control the error in TCP. First one is checksum, the second one is acknowledgement, and third one is retransmission. So in order to overcome the packet losses, we use these three techniques. Checksum field, which is nothing but if the segment if the segment is corrupted in a TCP, right, the particular packet will be discarded by the destination TCP, and it is considered as loss. So it will send a duplicate acknowledgement or negative acknowledgement so that the source device will retransmit the packet again. So this is called the checksum. So checksum is basically uh, the conversion of all the hexadecimal to binary of TCP header, and you can add together all the values, and the ones complement of the result will give you the checksum value, right? So if the um, checksum value of um, destination packet received at the destination is all zeros, then you can consider the received packet is correct, right? If the checksum is wrong, you can discard the packet and you can request for retransmission from the sending device. Then next one is acknowledgement, right? So TCP has another mechanism called acknowledgement to confirm the source device that the packet is delivered correctly, right? If the packet is not delivered, then uh, you can drag the, you can hold the acknowledgement so that sending device will retransmit the packet until the acknowledgement receives from the destination device, right? So when your segment is lost, damaged, or missing, you can request for a retransmission, right? So segments will be retransmitted only in the case of two events. When the first one is when the sender receives three duplicate acknowledgements, right? So when the sender receives three duplicate acknowledgements consecutively for a same segment, then the retransmission will occur. The second one is when a retransmission timer expires, right? So usually sending device will maintain a timer to monitor the acknowledgement packets, whether it is received or not, right? If the sending device doesn't receive the acknowledgement within the timer, right, time slot, it will start retransmitting the packet, right? So this is called a retransmission after timeout, right? Then next one is retransmission after three duplicate acknowledgement segments, right? So if particular uh, segment is not received properly, right? Uh, if your acknowledgement is lost, or if your RTO value is very small, right? So the retransmission will occur after receiving three duplicate acknowledgements for a particular segment. So this is a fast retransmission technique because it makes it possible to quickly retransmit the last segments instead of waiting for timer to end. So even though if a timer is not yet expired, but still after receiving three duplicate acknowledgements, you can retransmit the particular segment. The next one is TCP flow control. So TCP flow control uh, is basically the balance between the data production and the data consumption, right? So flow control means basically the receiver or the server will indicate the sender that I can able to receive this much amount of data, right? So for example, uh, sender sending host can able to transmit the data at a rate of 100 megabits per second, right? But the receiver is able to receive only 50 megabits per second. So the flow control is basically to indicate the sending device that I can able to receive only 50 megabits per second. During the connection establishment phase, the receiving device will indicate the sending device that I can able to receive only this much amount of data, so that you can set the transmission buffer accordingly. This is what we call it as flow control, TCP flow control. So otherwise, what will happen? Data loss. So I can able to receive only 50 megabits per second. Still, if you transmit at the rate of 100 Mbps, 50 Mbps data will be lost, right? So in order to avoid such traffic data loss, we are using TCP flow control, right? So it is a balance between the rate of data protection and the data consumption, right? So once you set up all the initial conditions, messages are transmitted from the sending device to receiving device, right? So TCP flow controls is applicable for any type of message transmission. For example, messages can be pushed from the sending application to TCP client, or message segment from a TCP client is pushed to TCP server, or you can server can pull the information from the TCP client, or client can pull the information from the another client, right? So in any possible way, flow control is the way of indicating the sending device that I can able to receive this much amount of data, right? So based on the buffer size available at the destination device, the uh, rate is fixed during the data initialization phase. This is called TCP flow control, right? TCP flow control. So for example, TCP flow control, we have a diagram here. See, so the first three number 1, 2, 3 indicates the connection establishment between the client and server. So sequence number, a unique sequence number is allocated for the synchronous message, for example 100, right? So the receiver window, here the receiver window is the buffer size allocated by the server, right, to the client, particular client. So I can able to receive 800. So even though the data rate set by the server is 800, the client will set data rate is equal to or less than the data rate defined by the server, right? Defined by the server. So once the connection establishment phase is over, the client will uh, transmit the data. So in the first phase, 200 bytes are transmitted. So now the receiver window is reduced because initially it is set up as 800. Now the window is shrinking up to 600, right? Uh, and then again, after getting the acknowledgement, client process will send the after 200 bytes. So initially 200 bytes are transmitted, then 201 to next bytes are transmitted. So this is how the data transfer will take place from client to server, right, until all the data are transmitted from the client to the server, right? So each segment will represent one mode of transmission, either acknowledgement or the data transfer or negative acknowledgement, right? So TCP flow control will ensure that all the messages are delivered to the destination properly, right? Properly. So TCP will guarantee the delivery of messages through acknowledgements, right? So as we discussed, TCP is a reliable protocol, so it will ensure that all the packets are transferred successfully to the destination, right, through acknowledgements, right? So if you don't receive the acknowledgement within the timer, or if you receive three duplicate acknowledgements, then the client process will start transmit the segment again. So it will hold the current data in a temporary buffer until it receives the acknowledgement, right? Once it receives the acknowledgement, then it will discard the packet and it will slide through to the next window, right? So this is how the flow control will work, right? So this is how the sliding of segment will take place from one window to next window, right? So silly window syndrome, one problem with the TCP flow control is silly window syndrome. So silly window syndrome is nothing but either the client machine will generate data slowly, or the receiving process consumes the data slowly, or both, right? So for example, the minimum header size required for TCP is 20 bytes, but your data production rate is 2 bytes, for example, I'm telling 2 bytes, then to transmit 2 bytes, you are wasting 20 bytes of header, right? So the efficiency of or utilization of resources is very poor in this case. This is called silly window syndrome, right? Silly window syndrome. So, so ultimate goal of any protocol is to utilize the resources properly. So instead of, in order to send 2 bytes of data, you are using 20 bytes of header. So the utilization of resources is very poor in this case. So in order to avoid silly window syndrome, you can accumulate the data. You can accumulate, you can wait for multiple data to gather, so that it should be more than the size of the header. Right? This is called Nagel's algorithm. Right? So you have to wait. All the data should be stored in a buffer for a particular period of time, or a particular, to gather the group of data in such a way that it is more than the header size, so that the utilization of resources will occur properly. This solution is called Nagel's algorithm, right? So first take segment of data will be sent irrespective of the size of the segment, right? Whether it is 2 bytes or 4 bytes, first segment is transmitted as it is. After that, you have to wait, right? Data will be accumulated in the buffer, right? So that in such a way that the utilization of resources will happen properly. The step will happen until all the data transfer is done. Right? So this algorithm is very simple, easy to implement, but it will create unnecessary delay. Yes, if you don't generate, if the sending device doesn't generate data at a quicker rate, then the waiting period will be very much longer, right? And a silly window syndrome, from the server point of view, if the server consumes the data slowly, right, then again it will create a problem, right? So the solution to this is called clock solution, right? Clock solution. So as soon as you receive the data, it will be stored in a buffer at the destination side, that is the receiver side. It will send the acknowledgement, right? It will send the acknowledgement to the sending device, right? Uh, irrespective of whether it is consumed by the particular protocol or not, right? As soon as the data is arrived at the temporary buffer, acknowledgement will be transmitted, right? So receiver window will be 0 if the receiver buffer is half empty, or if it accommodates maximum size of segments, right? And another solution to this is delayed acknowledgement. So the acknowledgement will be hold until the uh, segment is consumed by the particular protocol. That means the TCP protocol by the destination device, right? This is the solution two. The third one is error control, right? Error control. So error control, uh, to avoid error control, is a mechanism used by the TCP to mitigate packet loss, right? Packet loss. So we use checksum, acknowledgement, and timeout, right? So checksum is a 16-bit mandatory field, right? So we discussed in the TCP header, right? So the checksum field at the destination, if it is all zeros, then the packet is correct, right? If the checksum is invalid, the segment will be discarded, and either negative acknowledgement or um, retransmission request will be sent to the sending device, right? So instead of sending uh, acknowledgement for each and every segment, we can use cumulative acknowledgement or selective acknowledgement uh, to indicate that a particular group of segments are received properly, right? Properly, and no feedback provided for discarded, lost, or duplicate segments in the case of cumulative acknowledgement, right? Selective acknowledgement is used to report out of order or duplicate segments, right? Duplicate segments. So, what are the rules for TCP to generate acknowledgements, right? So, when a data is sent from the sender to receiver, acknowledgement provides the next sequence number, that is the next expected byte to be received, right? So that this results in less traffic and less number of segments transmitted between the sender and the receiver, right? So no delay will be there in the network traffic, right? So whether you are using single acknowledgement or cumulative or selective acknowledgement, the acknowledgement will be generated by the server machine, right? Server machine. So the retransmission will occur uh, uh, either after transmission timeout or invalid checksum, right? Invalid checksum or retransmission request, right? So retransmission after three duplicate segments is also called as uh, uh, Reno, right? Reno, because even if your timer doesn't expire, it will send a three duplicate acknowledgements. So once you receive three duplicate acknowledgements, you can transmit the particular segment again. This process is named as Reno, right? Out of order segments are not usually discarded by TCP. It will be held in the temporary buffer, right? For example, if you have received segment 1, 2, 4, right? So in this case, segment 3 is missing. So segment 4 will not be discarded, right? Segment 4 will be put in the uh, stored in the buffer. Once you receive segment 3 and 4 will be uh, given to the appropriate protocol, right? So TCP will make sure that all the segments are delivered in sequence to the process, right? So this is a simplified state machine model for TCP sender side, right? So sender will either be in ready state or blocking state, right? Ready state. So in ready state, you can start with you can transmit a segment, right? Once you transmit a segment, the client machine will enter into blocking state, right? So after getting the acknowledgement, it will again come to ready state, right? So sending device will be either be in ready state or blocking state, right? And this is a simplified state machine model for server side or receiver side. So receiver will always be ready to receive data from the client machine, right? So there are possible cases so that the change state will not change, but it will come back to the ready state, right, after some time. Third one is TCP congestion control, right? TCP congestion control. So congestion control to avoid overloading of network traffic, right? The client window size decided by the available buffer size of the server, right? Buffer size of the server. So RWND denotes the receiver advertised window size, right? Whereas CWND denotes the congestion window size, right? So the actual window size is equal to minimum of RV, receiver window size, and congestion window size, right? These are some abbreviations that we have used in the PPT: receiver window, congestion window, slow start threshold, maximum segment size, acknowledgement, and round trip time, right? So congestion window, we have two cases: slow start, exponential increase, right? So first the sender will transmit one segment at a time, right? One segment at a time. If it receives the acknowledgement for the particular segment, right, it will increase the segment size exponentially. So 1 plus 1 is equal to 2, right? So in the next phase, it will start transmitting two segments at a time, right? So it will, after getting the acknowledgement for the two segments, again it will increase the segment size by 2 plus 2, 4. Like this, the slow start will increase exponentially until it doesn't receive any acknowledgements, right? If it doesn't receive any acknowledgement after transmitting 8 segments, it will come back to half of the rate, 4, right? And it will start transmitting the segments, right? It will set the threshold value as such, right? So this is how slow start exponential increase will happen, right? So it will increase the segment size exponentially, right? The second one is additive increase, right? So the second one is uh, additive phase begins when slow start reaches threshold level. So if it reaches the threshold level, it will increase one by one. See, if you look at the diagram, you can easily understand. So it reaches the threshold level, which is equal to 4, right? So after getting acknowledgements for the first 4 segments transmitted, it will increase the segment size by 1. So 4 plus 1, 5. Next, it is after getting the acknowledgements for the 5 segments, it will increase again by 1. That is 4 plus 2 or 5 plus 1, right? 6, 7. Like this will increase additively, right? If it doesn't receive acknowledgements at a particular point of time, again it will reduce the segment size by 50%, right? For example, at 10 segments uh, transmission, we don't receive acknowledgement, it will reduce the segment size by 5, and it will retransmit the packet segments again. So this is how the uh, additive increase will take place, right? So this is an example. Maximum window size is 32. Let us take for example threshold is 16, right? The receiver window starts from 1 and grows exponentially till it reaches 16. After reaching 16, it will increase one by one. For example, when receiver window size is equal to 12, timeout occurs. That means you will not receive any acknowledgement. So it will decrease the segment size by 50%. That means 10. Then it will start transmit again one by one. This is how the uh, transmission will take place, right? So this is all about TCP and a computer network, right? Hope you enjoyed the video. Thank you, guys. Thanks.